You know, there is this incredibly specific, almost physical heartbreak in the world of algorithmic trading.
Oh, yeah. The absolute worst.
Right. It's a feeling I think literally anyone who has ever written, a single line of code for a market understands deep in their bones. Let's just paint the picture here for you.
Please do. I've been there too many times.
Yeah, so you've just spent weeks, maybe months, huddled over your keyboard in the dark. You are staring at a Jupyter notebook. You're just swimming in data frames.
Yeah, it's endless rows of data, yeah.
Exactly. And you finally finish coding your simulated strategy, optimizing every single parameter. You hit run on the backtest, and the results that come back are, well, they're nothing short of beautiful.
The dream scenario.
We're talking about a Sharpe ratio north of 2.0. Your maximum drawdown is sitting at a mere, -8% over a multi-year period. Your projected P&L is printing this steady, perfect, upward-sloping equity curve.
You basically feel like an absolute genius at that point.
You do. You feel like you have cracked the code. So you spin up an AWS instance, you secure your API keys, set up your webhooks, and you go live. You deploy the bot with real capital, expecting the market to just, start handing you free money based on the mathematical certainty of your simulation.
And that exact moment of deployment is where the honeymoon abruptly ends for, well, pretty much every uninitiated quantitative trader.
It's brutal because you fast forward just 1 month later and you excitedly log into your dashboard to check the live metrics. You're probably expecting to be planning an early retirement, right?
Obviously, yeah.
Yeah.
Checking real estate listings.
Right. But instead, you look at the real world numbers and you just freeze. The live P&L is 40% lower than what the backtest promised, the drawdown. It's completely blown past that safe -8%. It's like 1.5 times deeper.
And the trades. Don't forget the trades.
Yeah. Oh, man. Perhaps most maddening of all, you look at the raw trade logs and you realize that a massive chunk of the trades your backtest said would happen, maybe 20% of them just simply vanished.
Yeah. Poof. Gone.
They never executed at all. The signals were there, the market conditions were identical, but the reality was completely different. And your immediate knee-jerk reaction is always, I must have a bug in my logic. Or worse, you start going down the conspiracy rabbit hole of the market regime has changed in the last 30 days, the algorithms are hunting my stops.
It is such a common, almost inevitable psychological trap, honestly. But the foundational truth we need to establish right here, right at the very top of this deep dive, is that this discrepancy is almost certainly not a bug.
Wait, really? Not a bug?
No, not a bug in the traditional sense.
And
it is absolutely not the market suddenly changing its behavior just to spate your specific retail algorithm.
Yeah.
I mean, the market isn't malicious, and your code logic might actually be perfectly sound.
Then what on earth is happening?
What you are experiencing is a systemic architectural divergence. The harsh reality, and this is tough to swallow, is that your backtesting environment and your live trading bot are fundamentally two entirely different software products. Yeah, they are two distinct computational systems trying to model the exact same physical reality, but they are doing it using completely different physics.
Okay, let's unpack this. Because transitioning from that emotional pain of a failing bot to a structured clinical analysis of why it fails is exactly what our mission is today. We are taking a deep dive into an incredibly detailed taxonomy of, what do they call it, backtest-live divergences?
Yeah, that's the industry term.
Right. Heavily informed by the technical breakdowns from researchers like Sunat, who treat this not as some mysterious dark art, but as a completely solvable engineering problem.
Which it is. It totally is.
And our goal for you today is to arm you with the architectural patterns, the checklists, and the deep infrastructural understanding needed to bridge this massive gap between your simulated equity curve and your actual wallet. We are going to deconstruct exactly why a system that prints money in a pandas data frame bleeds money on a live exchange.
To do that effectively, we have to stop looking at, the bot as a single entity and start looking at the entire pipeline, like top to bottom.
Okay, so where do we start?
We can categorize the failure points into 4 distinct architectural layers. You've got data, execution, logic, and costs. If we systematically dissect how each of these layers models reality differently in a backtest versus a live environment, we can finally move away from the "it worked in backtest" syndrome. We can actually start engineering systems that are structurally sound.
That makes a lot of sense. So let's dive right into the first layer of the stack, data divergences. Before a bot can execute a trade, before it can even evaluate a single line of your alpha logic, it has to ingest a view of the market.
Exactly. It needs eyes.
And the immediate realization here is that the historical reality your backtest ingested is a perfectly sanitized mirage compared to the messy, fragmented reality your live bot consumes.
What's fascinating here is how insidious this specific divergence is. It's not the biggest killer of your P&L. I mean, we'll get to execution later. That's the real monster. But data divergence is a constant invisible friction. It acts as a slow bleed on your strategy's expectancy.
So what's the root cause of that bleed?
Well, it usually starts with something as deceptively simple as timekeeping.
Timekeeping, like timestamps.
Yep, timestamps. When you are backtesting, you download a CSV or query a database of historical OHLCV data. Every single row has a pristine, perfectly sequenced timestamp. But in the wild, interacting with live exchanges, time is entirely subjective.
Okay, subjective how? A minute is a minute, right?
You'd think so, but it is completely inconsistent across the industry. Let's look at how a one-minute candle is actually built. One exchange's matching engine might assign the timestamp for that candle at the exact millisecond the minute begins.
Okay.
But another exchange might assign the timestamp at the exact millisecond the minute ends. And it gets way more complicated when you factor in how you are receiving that data.
Right, because you have to actually fetch it.
Exactly. If your live bot is pulling a REST API for candle updates, which, by the way, is extremely common for mid-frequency strategies, that API architecture introduces inherent lag. The exchange's matching engine has to finalize the candle, write it to a database, and then your HTTP GET request has to hit the load balancer, query that database, and return the payload.
That sounds like a lot of steps.
It is. That process routinely introduces a 1 to 3 second delay after the actual physical close of the candle.
But wait, let me push back on this for a second. Let's assume I'm running a fairly robust trend-following strategy, right? Maybe I'm operating on 5-minute or 15-minute timeframes. Is missing 1 or 2 seconds of data or having a timestamp off by a fraction of a second really that big of a deal? I mean, the general macroeconomic trend of the asset hasn't changed in 2 seconds.
I get that logic. It might not seem like a big deal for a long-term moving average, but it is a massive vulnerability depending on the specific threshold triggers in your logic.
Okay, give me an example.
Well, a lot of algorithmic strategies rely on absolute precision at the boundaries. Imagine a strategy looking for a breakout above a major resistance level, or an RSI crossing exactly above the 70 line. In these scenarios, the market isn't static during those missing 1 or 2 seconds. A fraction of a pip movement during that API delay is the sole determinant of whether your Boolean logic evaluates to true or false.
Ah, I see the trap. Because the bot makes binary choices based on exact floating point numbers. It doesn't understand close enough?
Precisely. Let's say your live API delayed the candle data by 2 seconds. During those specific 2 seconds, a microburst of volume pushes the price just below your breakout threshold.
Oh, no.
Yeah. Your live bot evaluates the data, sees no breakout, and stays flat. But your backtest was built on a downloaded historical file where the data provider already aggregated that minute perfectly. The historical file recorded the high of that minute, which did cross your threshold.
So your backtest logs a wildly profitable entry while your live bot did absolutely nothing.
Exactly. You start accumulating these tiny split-second disagreements over thousands of candles, and suddenly your win rate is fundamentally skewed.
And it isn't just the timestamps drifting, right? The actual price aggregation itself can be different. When a historical data provider packages up months of tick data into manageable CSVs, they often use different aggregation logic than the live exchange does in its real-time WebSocket feeds.
Oh, yeah. The discrepancy often hides in the very last decimal digit of a price. Real-time exchange feeds are often optimizing for extreme throughput, meaning they might truncate a floating point number at the 8th decimal place to save bandwidth on a WebSocket broadcast.
Just to keep things fast.
Right. But a historical data provider running offline batch processing jobs might round that same number to the 10th decimal place. Again, if your live bot logic dictates buy if price is strictly greater than X, and the truncated live feed says the price is exactly X, while the historical feed says X.0001, you have a hard divergence. The backtest enters, the live bot ignores.
Man, that brings up the infrastructure itself, too. In a historical CSV, there are no blackouts. The data is a continuous, unbroken block of perfection. If there is ever a missing second of trading due to an exchange outage, the historical data provider usually just interpolates it, right?
Yeah, they mathematically smooth a line between the gaps so your pandas data frame doesn't throw a key error. It's totally fake data at that point, but it looks clean.
But live trading doesn't have the luxury of interpolation. You are relying on WebSocket's streaming data over the open internet. And I mean, the internet's hostile. TCP connections drop, network packets get lost in BGP routing black holes.
Oh, absolutely. Or an exchange's WebSocket server gets overloaded during a flash crash and silently drops connections without sending a close frame. Your live bot might suddenly sit there for 30 seconds, totally blind to the market, before the heartbeat timeout triggers and forces a reconnection.
And during those 30 seconds of blindness, the market is usually experiencing the exact peak volatility that your strategy was designed to trade.
Exactly. The backtest never experienced a 30-second blackout. It assumes perfect omniscience, 100% uptime, and zero packet loss. When you combine the timestamp drift, the aggregation rounding, and the network dropouts, this data category alone quietly bleeds roughly 2 to 5% of your annual P&L. It's death by 1,000 infrastructural paper cuts.
Wow. Which is painful, but I guess survivable. But that brings us to the second layer of the stack. If data divergence is a slow bleed, execution divergence is a gaping, catastrophic wound. We are moving from how the bot sees the market to how it actually interacts with the matching engine.
Right, execution divergence is where the vast majority of simulated profits go to die. The core architectural illusion here is the assumption that a backtest simulates an order fill perfectly.
Yeah, because if your vectorized backtest says buy at 100, it simply injects a synthetic trade at exactly 100 into your equity curve.
But reality is a completely different beast governed by the physics of order books.
Let's break down the most notorious villain in this category then, slippage. It's a term every trader uses, but the mathematical reality of modeling it is brutal. In a backtest, a market order fills entirely at the close price of the signal candle. But in reality, when your bot fires a market order, you are not buying at a single price, are you?
Not at all. You are eating into the liquidity of the order book. You're aggressively taking liquidity. Let's look at the mechanics of the limit order book or the L2 data.
Okay, walk me through it.
Imagine you place a $50,000 market buy order on a mid-cap asset. The backtest says the price is $50. But on the live exchange, there might only be $10,000 worth of limit sell orders sitting exactly at $50. Once your order consumes those, the matching engine moves to the next best price, maybe $50.05, and consumes the liquidity there, and then moves to $50.10.
So you are basically chewing through the asks.
Yes. Your final fill price is a volume-weighted average of all those different price levels you chewed through. On a $50,000 order, your average entry price might end up being $50.15. That 15-cent difference is your slippage, and it completely destroys thin margin strategies.
The technical research actually provides a cumulative slippage formula for this, which really visualizes the structural damage. So the total slippage over a series of trades is the sum of the size of each trade multiplied by the specific slippage of that individual trade.
Right.
And that individual trade slippage is roughly the order volume divided by the available liquidity at that exact microsecond, multiplied by an asset-specific impact coefficient.
Exactly. And what is absolutely crucial to understand about that formula is that the denominator, the available liquidity, is highly dynamic. A naive backtest assumes infinite liquidity at whatever the close price was. But in the live market, the depth of the order book at 2 a.m. on a Sunday is drastically different from the depth at 9:30 a.m. on a Tuesday during the New York Open.
Oh, for sure.
So if your bot attempts to execute a large position size when the order book is thin, the slippage isn't linear, it's exponential.
Man. And while slippage is actively eating your profit margins, the actual physics of time are also working against you. Let's talk about latency, the literal physical time loss. When I was reviewing the breakdown of this, the microsecond accounting was staggering. First, you have computation time, right?
Right. It might take your Python script 1 to 50 milliseconds just to evaluate the incoming WebSocket frame, crunch the indicators, and generate the order payload.
Then you have transmission time, which is governed by the speed of light and fiber optic routing. It takes 10 to 200 milliseconds for your JSON request to travel from your AWS server through the public internet into the exchange's API gateway.
And finally, matching time. It takes another 1 to 10 milliseconds for the exchange's internal risk engine to validate your margin and route your order into the actual matching engine core.
So when you add all of that up, you could be looking at a quarter of a second delay from the moment the market moved to the moment your order actually rests on the book.
Which is an eternity in trading. In a backtest, latency is absolute zero. The signal occurs, and the trade executes in the exact same computational cycle. In reality, during that quarter of a second, high-frequency market makers, Collocated institutional algorithms and arbitrage bots have already reacted to the exact same market catalyst your bot saw.
So they beat you to it.
Completely.
Yeah.
The liquidity you thought you were going to take has been pulled.
Right.
The price has already moved.
Okay, here's where it gets really interesting for me, and honestly, it completely shattered my mental model of how limit orders work. Let's talk about queue priority and partial fills. Because if I'm running a standard backtest and I set a limit order to buy an asset at exactly $100, and the historical data shows the price dropped to $100 for 1 minute, my backtest assumes I got filled, boom, I own the asset at a great price.
Yeah, it is the most logical assumption a developer can make. But architecturally, it is completely false.
It's like standing in line at an exclusive concert venue. If the ticket price hits my limit in a backtest, I assume I'm instantly inside the venue enjoying the show, but in reality, I'm just standing at the very back of a massive block-long line outside the doors. Just because the venue opened the doors doesn't mean I got inside before they reached capacity.
That analogy perfectly captures the mechanics of the matching engine. The limit order book operates on a strict first-in, first-out basis FIFO.
Yeah.
When your bot places a limit order at the best bid price of $100, you do not jump to the front of the line. Your order is placed sequentially behind every single other trader, market maker, and algorithm that placed an order at that exact $100 price level before you did.
So the market price can technically touch my limit level without me getting the asset.
Absolutely. The market might trade quite a bit of volume at $100. But if that incoming sell volume wasn't large enough to chew through the massive line of resting limit orders ahead of you in the queue, your specific order never executes. The selling pressure dries up, the price reverses back to $101, and you are left holding nothing but open cash.
Meanwhile, my backtest, completely unaware of this FIFO concert line, cheerfully records a 100% successful instant fill and adds the simulated profit to my equity curve.
Yeah, we refer to this in quantitative engineering as the price touched equals order filled fallacy. It is the single biggest lie a backtest tells you. Standard backtests aggressively overstate fill rates for limit orders.
And what if I do get to the front of the line?
Even when you do get to the front of the queue and get filled, it is very often a partial fill. Your backtest assumes your entire $50,000 order was filled instantly. In reality, maybe you only got $10,000 filled before the remaining liquidity evaporated and the price moved away.
Oh, so you're just stuck with a weirdly sized position.
Exactly. Your bot is now sitting with a severely undersized position. Your risk management math is skewed, your profit targets are misaligned, and your bot is operating in a state of partial exposure that the backtest simply never modeled.
It is terrifying when you actually map out the mechanics. The research indicates that execution divergence alone, latency, slippage, and queue priority can obliterate anywhere from 10 to 30% of your annualized P&L. So just between data drift and execution reality, we could already be down 35% from our simulated dreams, and we haven't even looked at the code yet.
Which is the perfect pivot. We've blamed the data vendors, we've blamed the exchange's latency, we've blamed the FIFO order book, but eventually you have to look at your own architecture. The third layer of the stack is logic divergences, the internal saboteur.
So we're talking about the code actually fighting itself?
Yes. The most pervasive trap here is an architectural flaw known as the separate codebase's anti-pattern.
This sounds so incredibly innocent when you first start building trading systems.
Mm-hmm.
You have a file, let's call it backteststrategy.py, sitting in your research folder. You iterate on it, you tweak the indicators, and you get those beautiful results. Now you need to hook it up to the live exchange. So you create a brand new file, let's call it livebot.py, and you diligently copy and paste the logic over.
Right. It feels clean. But then the reality of software maintenance sets in. A week later, you notice a small, weird bug in the live bot. Maybe the exchange's API throws an unexpected JSON key error during weekend maintenance hours. So you quickly patch the livebot.py file with a try except block to ignore weekend data anomalies.
Yeah, standard bug fixing.
But you are tired, and you forget to port the specific patch back to the backteststrategy.py file.
Or, conversely, you are doing weekend research and you come up with a brilliant new volatility filter. You test it in the backtest file, it drastically reduces your drawdowns, but you get busy with your day job and forget to deploy that specific algorithmic tweak to the live bot on your AWS server.
Precisely. After 3 or 4 months of these tiny micro-edits, hotfixes, API patches, and parameter tweaks, the two code bases have completely drifted apart on a genetic level. They are effectively two entirely different trading strategies. You continue to run your backtest locally, thinking it accurately represents your live bot's behavior, but they are evaluating the market using completely different rule sets.
Now, I have to challenge this because I know what every listener is thinking right now. They're thinking, I am a meticulous developer. I use Git. What if I enforce a strict personal rule that I flawlessly copy-paste my code perfectly every single time I make a change? Can extreme developer discipline overcome this anti-pattern?
What's fascinating here is that even with absolute robotic discipline, even if your logical equations are a carbon copy, you will still fail.
Wait, really? How?
And the reason comes down to the fundamental physics of the underlying software frameworks you're using. Let's look at how backtesting actually works under the hood. It is almost exclusively done using vectorized libraries like pandas or NumPy and Python. Vectorization means the CPU processes entire columns of data simultaneously using optimized C-level SIMD instructions. It iterates over massive arrays of historical data all at once.
Right. It has the luxury of looking at the entire history of the asset in one giant chunk of memory.
Yes, but a live trading bot operates in a totally different paradigm. A live bot is built on an event-driven framework, heavily utilizing asynchronous loops like Python's Asyncio. It doesn't have an array of history. It sits idle, waiting for a single atomic event like a new WebSocket message or an order execution confirmation, and it reacts to it sequentially, one tick at a time. Even if your core mathematical formulas are identical, vectorized architecture and event-driven architecture handle edge cases entirely differently.
Give me a concrete example. How does the exact same code produce a different result just because one is an array and one is a loop?
Let's talk about how they handle not a number or NaN values, which happen all the time when calculating rolling indicators. In a vectorized pandas data frame, if a moving average calculation throws a NaN for the first 50 periods, pandas often just silently ignores it or forward fills it, allowing the backtest to continue smoothly.
Okay, pretty forgiving.
But in a live event-driven bot, if your logic tries to execute a mathematical comparison against a NaN value that just arrived via WebSocket, it will often throw a fatal type error exception and crash the entire bot.
Oh, wow.
Or consider the order of operations during high volatility. Imagine a single 5-minute candle has a massive wick that technically crosses both your stop-loss price and your take-profit price within the same candle.
Ah, the classic Schrodinger's trade. Did I win or lose?
Exactly. A vectorized backtest looking at OHLCV data has no idea which happened first. It just sees the high and the low. Depending on how the backtesting library is coded, it might arbitrarily resolve the take-profit first, recording a win in your simulation.
And the live bot.
But the event-driven live bot, connected to the actual tick data, watches the price hit the stop-loss first, executes the market sell, and hands you a painful loss.
That is maddening. So even identical code logic behaves differently because the physics of the environment vectorized memory arrays versus asynchronous event loops are fundamentally incompatible.
And that brings us to the most complex architectural difference of all, state management. A vectorized backtest is generally stateless. It's just iterating over historical arrays, oblivious to any external reality. It doesn't need to remember anything other than the current row it's on. A live bot, however, is intensely stateful. It has to constantly manage active positions, monitor available wallet balances, track nonces for API security, and manage dictionaries of open order IDs.
So what happens when the inevitable occurs and your AWS server reboots or your Python script crashes due to an out-of-memory error?
That is the ultimate nightmare scenario for state management.
Yeah.
When a stateless backtest restarts, you just run the script again, and it instantly rereads the CSV from row 0.
Yeah.
When a stateful live bot crashes and restarts, it wakes up with total amnesia. It has no idea what it was doing 3 seconds ago.
It's just blank.
Completely. Did it have an open limit order?
Yeah.
Did that order get filled while the bot was offline? The bot now has to painstakingly query the exchange's REST API to rebuild its internal state dictionary. If the exchange API rate limits your bot during this reboot, or if an order fills while the bot is trying to sync, you get state desynchronization. Meaning the bot might think it has no open positions and fire a new buy signal, double exposing your capital. A backtest simply cannot model the chaos of state recovery. This category of logic and architectural clashes accounts for another massive 5 to 20% P&L gap. Developer disciplines simply cannot overcome fundamental structural differences.
So even if you are a coding monk, the framework will eventually betray you. Okay, let's move to the fourth and final category of divergence, the silent tax. Cost divergences. Let's play a hypothetical game. Let's say your data ingestion is perfectly synchronized, your execution model uses flawless L2 order book simulation, and you've somehow solved the state management crisis. There's still an invisible structural tax dragging down your profitability.
This category is unique because it's entirely predictable, yet developers routinely ignore it. The most glaring financially devastating omission in algorithmic backtests is the failure to model funding rates, specifically if you're trading perpetual futures contracts in the crypto markets.
So what does this all mean in practice? Let me do the math on this out loud, because when you actually calculate the drag of funding rates, it is genuinely shocking.
Yeah.
Perpetual futures use funding rates to peg the contract price to the spot price. If the market is heavily long, longs pay the shorts. Let's say you are trading a trend-following strategy with 10 times leverage, which is pretty standard for these markets.
Yeah.
And let's assume you are holding a long position during a bull market where the average funding rate is 0.01% charged every 8 hours.
Which, to be clear, is a very conservative baseline rate. During volatile bull runs, it can easily spike to 0.05% or higher. But let's stick with the baseline.
Right. So you take that 0.01% and you multiply it by 3 because you are charged 3 times a day. That's 0.03% a day. Multiply that by 365 days in a year. You are at 10.95%. Now, because this is charged on your total position size, you have to multiply that by your 10x leverage. That translates to 109.5% per year.
Yeah.
Just to hold the position. That is a silent, constantly ticking fee that is actively draining your margin balance. This oversight alone can completely bankrupt a strategy that looks like a runaway winner in a backtest that simply assumed holding a position was free. A 109% annual headwind is more than the total gross profit of most highly successful quantitative strategies.
It is the silent killer of leverage. And funding rates are just the tip of the cost iceberg. Most traders remember to include basic trading commissions in their backtest, but they almost always use the wrong structural rates. They model a flat 0.1% fee, but they don't account for the crucial difference between maker fees and taker fees.
Explain how that impacts the bot's behavior.
Well, if your bot uses limit orders that rest on the book, it is providing liquidity. It is a maker. Maker fees are often drastically lower, sometimes even negative, meaning the exchange pays you a rebate. But if your bot uses market orders or crossing limit orders, it is taking liquidity. It is a taker. Taker fees are significantly higher.
Okay, so if the backtest gets that wrong.
Exactly. If your backtest assumes you are getting the cheap maker fee, but your live bot's logic is constantly triggering aggressive market orders that incur the taker fee, your cost projections are completely divorced from reality. Furthermore, backtests rarely model exchange VIP tiers or the massive trading fee discounts you get for holding native exchange tokens.
And then there is the inescapable reality of the bid-ask spread itself. A standard naive backtest only sees one price, usually the close price of the candle. It assumes you can magically buy and sell your entire position at that exact single number.
But in the physical reality of the market, there is no single price. There's only the best price someone is willing to buy at, the bid, and the best price someone's willing to sell at, the ask. The close price might be printed as $3,000, but the actual order book shows a best bid of $2,999.50 and a best ask of $3,000.50.
You are never, ever buying at the close.
Never. If you want into the market immediately, you are buying at the ask. If you want out, you're selling at the bid. Every single time your bot transacts, it must cross that spread. You're paying half the spread to enter the position and the other half to exit. Over a few trades, it's negligible. Over thousands of high-frequency trades, crossing the spread will entirely consume a thin margin strategy.
Let's synthesize everything we've covered in these first 4 layers, because the picture it paints for the retail algorithmic trader is incredibly grim. We have timestamp drift and network blackouts. We have latency, slippage, and FIFO-Q priority denying our fills. We have vectorized pandas data frames clashing with asynchronous event loops. And we have the silent compounding grain of funding rates and spread crossing.
And the most terrifying part of this entire taxonomy is what quants call the cumulative effect. These divergences are not random variables that magically cancel each other out over time.
No, they are highly directional, frictional forces.
Exactly. They act simultaneously, and they almost universally act in one specific direction against your profitability. The structural math is unforgiving. Your live P&L is approximately equal to your backtest P&L minus the delta of data drift, minus the delta of execution drag, minus the logic errors, minus the hidden costs.
So when you rigorously tally all of that up across thousands of trades, a 20 to 50% divergence from your simulated backtest P&L isn't just possible, it is the mathematical baseline for an unrefined architecture.
It is completely normal. And if you're using leverage, that frictional drag is multiplied, which is precisely how you go from a simulated 80% annualized gain to a live margin call in 30 days.
Okay, deep breath. We have thoroughly, painfully diagnosed the disease. We've quantified the expected structural losses. But now this deep dive pivots to the cure. This is where the engineering actually gets actionable, because top algorithmic trading firms and institutional quants aren't just crossing their fingers and hoping the market is nice to them. They build specialized infrastructure specifically designed to eliminate these exact divergences.
Right. We're moving from diagnosis to architectural design. There are distinct engineering patterns that solve the problem of your simulation and your live bot drifting apart. The overarching goal of every single one of these architectures is unification.
Let's start with the most accessible solution. Pattern 1, the shared core. This seems like the most intuitive, immediate fix to the separate code bases nightmare we discussed earlier, where you have a backtest.py and a live.py that eventually diverge.
The shared core is the foundational step toward institutional parity. The concept relies heavily on dependency injection. You take the absolute brain of your strategy, the mathematical logic that calculates indicators, evaluates signals, and makes the Boolean decision to trade, and you extract it into a completely independent, isolated software module. The shared core becomes a standalone entity that is imported and utilized by both your backtesting engine and your live trading script.
I love the analogy used in software engineering for this. The shared core is essentially a brain floating in a jar. It has absolutely no idea if it's plugged into a virtual reality simulation, like your historical backtest, or if it's plugged into a robotic body walking around the real world like your live exchange bot. It doesn't know, and more importantly, it doesn't care. It just blindly processes whatever sensory input it's fed through the jar.
That is a brilliant visualization of dependency injection. The golden rule of the shared core pattern is strict isolation. The core module must never contain hard-coded API keys, it must never import exchange-specific libraries, and it must never know where its orders are going. It simply exposes a function. It receives a standardized OHLCV candle or tick event, it crunches the math, and it returns a standardized order request object.
So the rest of the code just wraps around it.
Yeah, the surrounding infrastructure layer, the adapters, is what handles the messy reality. The backtest adapter feeds the brain the historical CSV data and intercepts the order request to fake an execution. The live adapter feeds the brain real-time WebSockets and translates the order request into a cryptographic API payload for the exchange. But the logic, the brain in the jar, is strictly mathematically unified. You literally cannot have logic divergence because there is only one file making the decisions.
Now, this shared core is usually built in Python, which makes it highly accessible for most traders. It has relatively low implementation complexity. But the engineering consensus is that this only achieves medium parity. Why is a perfectly unified brain only getting us to medium parity?
Because while you have completely fixed the logic divergence, you're still fundamentally at the mercy of Python's inherent computational limitations when it comes to simulating the physics of execution. Python, due to the global interpreter lock and its dynamic typing, simply isn't fast enough or deterministic enough to perfectly simulate high-frequency, microsecond-level order book dynamics. Which brings us to the heavy artillery. Pattern 2.
Right, pattern 2, event-driven unification. And we need to specifically unpack the Nautilustrator approach here, because this is where we leave retail scripting behind and enter institutional-grade architecture.
Nautilustrator solves the parity problem by abandoning Python for the core processing loop entirely. It built a unified kernel, a core matching and execution engine written in Rust.
Let's pause on that because language choices in architecture are rarely arbitrary. Why Rust? Why not just use faster Python libraries or C++?
To understand the shift to Rust, you have to understand the terror of garbage collection.
Garbage collection.
Yeah, in languages like Python, Java, or C#, the system periodically pauses all execution to clean up unused memory. This is called garbage collection. These are known as stop-the-world pauses. They might only last a few milliseconds, but they introduce massive, unpredictable latency spikes. In a backtest, a 10-millisecond pause doesn't matter at all. But in live trading, if a flash crash occurs and your bot attempts to fire a massive market order, but Python decides to initiate a garbage collection pause at that exact microsecond, you are dead in the water.
That's horrifying.
Rust eliminates this entirely. Rust uses a strict ownership and borrow checking model for memory management and compile time, meaning there is no garbage collector. It provides the memory safety of high-level languages with the deterministic, nanosecond resolution performance of C. There are no stop-the-world pauses.
And the throughput metrics are staggering. You can process millions of rows of market depth data per second, handling data structures that don't even fit into standard RAM. But the real magic of this architecture isn't just the speed, it's how it structures the flow of data using hexagonal architecture.
Yes, hexagonal architecture, also known as the ports and adapters pattern, which was pioneered by Alistair Cockburn. It takes the brain-in-a-jar concept and elevates it to an enterprise standard.
Unpack ports and adapters for us, because structurally, how does this actually force the backtest and the live bot to behave identically?
Think of the core trading engine, the Rust kernel, as the hexagon in the center. The hexagon defines rigid, standardized interfaces or ports for how data can enter and how orders can leave. You then build adapters that plug into these ports. You have a historical data adapter that reads CSVs and a live WebSocket adapter that reads Binance or Coinbase feeds. Because the engine is entirely event-driven, the processing sequence is strictly deterministic. That means if you run a backtest, every single event, every price tick, every internal order placement, every simulated fill is processed in the exact same computational sequence it would be in a live environment. We call this being bit reproducible. The backtest isn't just simulating the market, it is simulating the exact state machine of the live bot. Furthermore, institutional setups use identical infrastructure backing both environments, utilizing Redis for high-speed caching and message queuing, and PostgreSQL for state persistence, whether it's live or simulated.
So the backtest and the live bot aren't just sharing a brain, they are operating in identical, mathematically deterministic universes. It has high implementation complexity. I mean, learning Rust and event loops is steep, but it achieves maximum parity.
Exactly. But if rewriting your entire tech stack in Rust is too daunting, there's a very pragmatic middle ground. Pattern 3, the strategy interface approach.
And this is specifically highlighting frameworks like free trade.
Free trade is brilliant because it forces architectural discipline within Python. It forces you to build your strategy by inheriting from a unified iStrategy class. By standardizing the object-oriented interface, the framework guarantees that the exact same class definition runs in both the vectorized backtester and the asynchronous live bot. The framework itself handles the messy translation between pandas arrays and live tick data, hiding the state management complexities from the developer.
And what really caught my eye with free trade is how they tackle execution divergence with a feature called time frame detail. This feels like a massive leap over standard pandas backtesting.
It is their specific solution to the price touched equals order filled fallacy we discussed earlier. If your strategy operates on 1-hour candles, a standard backtest just looks at the high and low of that hour and assumes fills. Time frame detail fundamentally changes the simulation.
Oh, so
It dynamically downloads the underlying 1-minute or even tick-level data that makes up that specific 1-hour candle. It then steps through that microdata internally to simulate exactly when the price hit your limit order within that hour and what the sequence of events actually was. Did the 1-minute candle hit your stop loss before it hit your take profit? The detailed time frame resolves the Schrodinger's trade.
which perfectly bridges us to the final and perhaps most mathematically intense layer of our deep dive, the art of simulation. Because even if you have the perfect hexagonal Rust architecture or a brilliantly configured free trade instance, you still have to mathematically simulate the physical messiness of live markets inside that architecture. How do we accurately fake a trade?
This is where we separate the amateurs from the quants. We can categorize Phil's simulation into 3 distinct levels of maturity. Level 1 is the naive level.
Right. The price touched 100, therefore my massive order is filled instantly with zero slippage. We already established this is the fastest way to bankrupt yourself.
So developers quickly move to level 2, the fixed slippage model. This is where you configure your backtester to assume every single trade suffers a flat penalty, say 5 basis points of slippage. It's incredibly crude. The algorithm doesn't care if you are trading $10 in a highly liquid market or $10 million during a Sunday night low-volume session. It just applies a flat tax. It's better than nothing, but it completely ignores the physical reality of market liquidity and order book depth.
Which leads us to the gold standard, level 3, adaptive drill down and market impact modeling. This isn't just about looking at 1-second tick data. This is about simulating the actual L2 order book. And to do that, you have to understand the math of market impact. Let's break down the Almgren-Kris model.
The Almgren-Kris framework is foundational to institutional execution algorithms. It doesn't just ask, what is the price? It asks, how much will the price move because I am trying to trade? It breaks market impact down into two components. Temporary impact, which is the immediate slippage you incurred chewing through the resting limit orders, and permanent impact, which is how your aggressive order signals information to the market and causes market makers to permanently reprice their quotes.
Let's look at the variables in the simplified temporary impact formula because the intuition here is beautiful. The change in price, the slippage, is driven by volatility, multiplied by an impact coefficient, multiplied by the square root of your order volume divided by the total market volume.
Let's unpack why those specific variables matter. First, volatility. If the market is already highly volatile, the order book is usually thin because market makers widen their spreads to protect themselves. Therefore, your order will chew through the book much faster, causing massive slippage. Second, the ratio of your order size to the total market volume. If you're trying to dump a whale-sized position into a tiny, illiquid altcoin market, you are going to absolutely crater the price.
But the absolute key detail in that formula is the square root, isn't it?
Exactly. The relationship between order size and market impact is not linear. It's concave. If you double the size of your order, your slippage doesn't simply double, it scales by the square root.
That's fascinating.
The order book has an inherent elasticity. It can absorb small orders with almost zero impact. But as the orders get larger, they penetrate deeper into the bid-ask spread, triggering cascading stop losses and forcing liquidity providers to retreat. Simulating this elasticity, actually calculating how your hypothetical order volume would mathematically consume the historical L2 order book, is the only way to achieve institutional-level divergence, which allows you to model your live P&L within a very tight 2 to 5% margin of error.
So the question you have to ask yourself right now if you are running any capital in these markets is, which level of fill simulation are you trusting? Are you running naive simulations and wondering why your live bot is bleeding? Or are you calculating square root market impact models?
And here's the final reality check. Even if you are calculating market impact with perfect mathematical precision, you still have to prove it empirically. Math is not reality until reality confirms it. This is where the absolute necessity of shadow mode comes in.
Shadow mode. Paper trading on steroids. Running your fully architected bot on live WebSocket data, logging every single signal, but purposefully disabling the final API call that sends real orders to the exchange.
Shadow mode is non-negotiable. You must run your live architecture in shadow mode for a minimum of 2 to 4 weeks before committing a single dollar of real capital. During this calibration phase, you are actively comparing your shadowbot's real-time logs against your backtest simulated logs, and you need a rigorous Grafana dashboard to track specific parity metrics.
The metrics required to pass shadow mode are brutal. You need a signal match rate of greater than 95%. Meaning 95 times out of 100, your backtest and your live bot agree perfectly down to the millisecond on when to enter and exit. You need to track average slippage per asset and trigger alerts if it deviates from your level 3 simulation. You need a fill rate parity of over 90%. And you must monitor the 99th percentile of latency. If it takes more than 500 milliseconds from the signal generation to the simulated fill acknowledgement, your entire architecture is fundamentally too slow for your strategy.
And shadow mode isn't just an auditing tool to find bugs. It is a calibration feedback loop. After accumulating a month of real-world slippage and latency data from the live market, you take those empirical numbers and you feed them back into your backtest's level 3 parameters. You are quite literally forcing your simulated environment to learn the messy, physical reality of the live exchange.
Let's zoom out and summarize this incredible journey we've taken through quantitative engineering. We started with the universal heartbreak of the "it worked in backtest" syndrome. We established that the 40% P&L drop isn't a bug, but a systemic failure to model the physics of the market. We deeply deconstructed the 4 core divergences: the timestamp drift and network gaps of data, the brutal latency, slippage, and FIFO-Q realities of execution, the code-based drift and state amnesia of logic, and the silent compounding drain of cost divergences like funding rates.
And from that rigorous diagnosis, we mapped out the architectural cures. We explored dependency injection via the shared core pattern. We unpacked the massive advantages of memory-safe Rust and deterministic event loops using hexagonal architecture. And finally, we realized that true simulation requires complex mathematical modeling, like the Almgren-Kris framework, and relentless empirical calibration through weeks of strict shadow mode monitoring.
It is truly a masterclass in quantitative systems design.
If there was one core philosophy you take away from this entire deep dive, it must be this. Perfect parity between a simulation and reality does not exist. It never will. A backtest is, by definition, a model of reality. And a model must, by its very nature, simplify reality to be computationally viable. If it didn't simplify reality, it wouldn't be a model, it would just be the universe itself. The goal of algorithmic trading is not zero error. The goal is controlled, predictable error. The difference between a 5% parity error that you explicitly modeled for and a 50% parity error that triggers a margin call is entirely determined by the rigor of your architecture. You must embrace a pessimistic backtest by default. It is infinitely better to aggressively penalize your expectations in the simulation and be pleasantly surprised by the resilience of your live trading than to suffer the reverse.
Assume the market will give you the worst possible queue position, the worst possible slippage, and the highest possible funding rate, and build a mathematical system that can still extract profit despite it all. But as we wrap up this deep dive, I want to leave you with a final, slightly provocative thought built on this very idea that perfect parity is mathematically impossible. We've established that models must simplify reality. We've established that institutional-grade, Level 3 adaptive L2 order book simulations using Rust kernels and deterministic event loops can get you down to a pristine 2% margin of error. But achieving that requires immense computational power, complex systems engineering, and constant daily calibration.
A massive undertaking.
Right. So at what point does the sheer economic cost in AWS server compute, expensive L2 data feeds, thousands of engineering hours, and developer sanity of calculating those institutional grade simulations actually outweigh the P&L saved by the trading strategy itself? Is there a hidden threshold, perhaps for mid-frequency swing traders, where a slightly flawed Python backtest, one that relies on a cruder level 2 slippage model but costs pennies to run and hours to build, is actually the most economically efficient way to deploy capital? When does the relentless pursuit of perfect architectural parity become a financial trap of its own making? Something to seriously mull over the next time you find yourself staring at a simulated Sharpe ratio of 2.1. Until next time.